Hello. I'm very glad to start this day, so let me bring my phone. Let me start with the first hour. Some lectures.
So negative 1/3. Now, does it look like something you can handle? You do have a fraction here, but the sum problem, it'll be very similar to the last problem. That's even, that's kind of nice, right? Tell me, think about it. I'll give you 10 seconds on your own. Think about, don't say it out loud. I want everyone to think of this. Think about what you're going to add to both sides right now. Just think about it. What are you going to add to both sides? Not 2. 4, not 16. Okay, let's start 10.1. That was a lot in this class. Okay. How do you, what's the whole process? When you think about it, these are fractions. If you have a, look at the board, if you have a different root, what you have is a different denominator. So the process of combining roots is the same process as finding a common denominator. That's it. That's really all this is. You're finding a common root. That's the same thing as saying a common denominator. That's what you do when you combine those fractions. You make them into fractions, find a common denominator, use that to add them together. It will give you a common root. Originally, I feel okay about what we've talked about so far today.
I got a question.
Yeah.
So, like, in the previous example where we would have 2 square roots, would that be the second step to actually get your final answer?
Yeah, except what's going to happen is most likely in this case, you probably get this back in. To the positive 3/4. I need you to notice that, yes, okay. There's a calculator method. Now I'm going to teach you a method in a little while, a couple sections from here, where we can simplify these numbers to get something that's still radical, but we can make that the radicand smaller by simplifying. Very similar to this idea. Okay, very similar. Sure. So we're going to leave that alone for now. So a couple notes that we just learned. If n is even, you cannot have a negative as part of your radicand or inside the one number to pick from, right? They're all 3. Just say 3. Yeah, that's your n, right? N's 3. It's an odd. What odds don't make everything positive. Therefore, we don't need an absolute value. How about that one? Does the power match the root?
Yep.
Do we need an absolute value or not?
Yes.
So there's no work here, folks, if it matches up. That again, I don't want you to answer out loud on these ones. I want everyone to think of this. Cube root of negative 64. But this asks us, what number times itself 3 times gives you negative 64? And we go, oh, there's a negative inside. No solution, right? No real real solution.
One of them's a negative, one of them's not.
Here just to make sure that you guys really see this. By the way, these don't take a whole lot of work. You're not even going to work on them. You're just going to cross stuff out and understand that one of them's going to have an absolute value and one of them's not. That's basically it. If it's even, it has absolute value around it. If it's odd, it doesn't. So let's do 6th root of x to the 6th. Firstly, does the power match the root, ladies and gentlemen? Yeah. Again, I want to refresh your memory on how to graph just the square root of x. But then I also want to graph the cube root of x. And we're going to do this with a table. Now, let's try some negatives here. Let's try -1 again and see if it's off. And I want you to see what I'm doing for this one. What do you think? The square root or the cube root? Square root. Every even type of root. 4th root, 6th root, 8th root, 10th root, will look similar to this. You'll have this general shape and only be one-sided because you can't plug in negatives. However, the higher you go up in your root, the flatter this will get. Okay? In order to get 2 out of the 4th root, you'd have to plug in 16. Go all the way over here. Okay, just to get the value of 2. It's going to flatten that out. It'll really flatten it. Every odd power root, 3, 5, 7, 9, will look something like this. It'll have this negative version as well, because you can plug in negatives to it. So it'll be some sort of a S curve. Now, the only thing we got to talk about is that the shifting still works. On your homework, it's going to ask you to make tables for all this stuff. I really don't care about that. If you want to make tables, great. But do you understand the shapes of these guys? If you understand the shapes, you can manipulate them by shifting them around. Now, for a 5th root or a 4th root, you might want to draw a table once, just to kind of see the values and how it looks. Okay, draw it one time, and then if it asks you to shift it, go ahead and shift it. So since we just graphed some of those things on your test, if I ask you to do f of x equals square root of x plus 1, like this, where it's inside of the radical, you should be able to tell me what type of a shift that is. Is that a shift up, down, left, or right? Firstly, let's determine whether it's a vertical or a horizontal shift. Now you tell me, is this plus 1 within the function or after the function? It's within. So is it a horizontal or a vertical shift? Remember, after would have been up or down. Okay? This is within the square root. That's why this little tail here is covering that plus 1. This is within the square root. So this is going to be a shift either left or right. Remember, my original graph looks like this. My original graph looks like that. What did the plus 1 do if it's inside of your function? Was that a shift to the right or a shift to the left? Which one was that? Left. That's right. That's correct. So this is a shift to the left. If it's inside, it was horizontal, and it was kind of backwards of what your head wanted to say. This was left 1. So here we said, oh, okay, let's move over. It takes one spot. Redraw our graph. We can shift these graphs around, just like we did before. Are you okay with this? Okay, let's try one more. Let's do g of x. Cube root of x plus 2. Cube root of x plus 2. course, you need to know what the shape of the graph looks like, which is why I'm going to have you draw at least one graph using a table for like a fourth root and a fifth root. But then after that, you can just shift them around. That's fine. What's this graph look like? Does it look exactly like this? No, it's got that other side to it. So the original one would look like that. Something like that. Can you tell me what this +2 does? Is the +2 within the function or after the function? So is it a horizontal shift or a vertical shift? Definitely, and it's going to go up or down. So this says you're going to take your graph, just move it up 2 spots. If we move it up 2 spots, we're going to redraw the same exact thing. And that's my new function. We can shift these things all over the place. We can do combinations as well. We can do something within the function and something after the function. We could even reflect it with a negative up front that would flip these things upside down. If you flip this upside down, notice you're going to get a Z curve instead of an S curve. You with me on this, ladies and gentlemen? How many understood what we talked about today? Good. Well, that wraps up our section 10.1. First name, not by the name. Root, any root that we've ever seen. So today we are going to talk about something called rational exponents. Now, when we say the word rational, what does rational actually mean? We've dealt with rational functions, right? Say that again. A fraction or something. Yeah, that's actually exactly what it means. It means a fraction. So rational means ratio or a fraction. So whenever we deal with rational exponents, this is going to seem kind of weird to you, but we're going to deal with exponents that are actually fractions. Isn't that kind of strange that we can have exponents that are fractions? Right now you've dealt with squares or cubes or fourth powers. You've never actually dealt with a fractional exponent before. That's what we're going to talk about today. So rational exponents. Now the interesting thing is that I just said you've never seen a rational exponent before, which is actually a lie. You have seen a rational exponent before. It's just that we haven't dealt with them as an exponent. Here's the whole deal about section 10.2 and why it's in this section that has all 2 of the radicals. Every single time that you've seen a root, a square root or a cube root or a fourth root, actually you've been dealing with a rational exponent. As a matter of fact, any root that we've ever seen can be represented as a rational exponent. I'm going to show you how right now. So write this down. Any root can be represented as a rational, that means fraction, rational exponent. Here's how. You remember talking about those nth roots, how we had like a radical like this, and then we had some sort of root out front. Now, what would that type of root be if I just left it like that? Square root. And if I had a cube root, what number would I put and where would I put it? Right, the little like indices part, the little crotch of this thing. Right there. That little thing. That's where I put a cube root. If I had a fourth root, I put a number 4 there. Or an nth root, or any root, I put a little n there. And whatever's on the inside, we're going to represent that with an a. So our radicand in this case is just a. Could be anything. Could be x squared plus 3. Could be whatever I want it to be. Here's the deal. This is kind of neat. Every single time you've seen something like this, this actually represents a fractional exponent. Here's how you write it. You have, in this case, our base is a. It's whatever our radicand is. An nth root of a is the same thing as a to the 1 over n power. That's how you change from a root into a fractional exponent. Weird, huh? Why are we doing that? How are we making these look like those? Well, tell you what. Do you know anything about exponents? If you multiply common bases, you add exponents, right? If you have an exponent to an exponent, you multiply. If you divide, you subtract. We can do all that stuff with our roots now. We couldn't do that here. It wouldn't make any sense to do that. But as soon as we translate to a fractional or rational exponent, we can do all those things that you already learned. That's why we're translating this. Let's see if we can manage to change some of these from this form back into our roots. Are you guys ready to try some of this? Okay, let's do this. So first one, let's say that we had 25 to the 1/2 power. 25 to the 1/2 power. You can notice a couple things about this. Firstly, where's our n go in our fractional exponent? Where's it go? Numerator, denominator? Denominator. And where's that 1 come from? I'll show you this right now. I'm not supposed to until later, but I'm going to give you a sneak peek, okay? Where this 1 comes from, what's the power of a right here?
1.
That's where the 1 comes from. Okay, so this little preview of where that number comes from. Right now, it's just a. The first power, that's why we have a little 1 right there. You guys okay with that? So question, can I represent 25 to the 1/2 as a type of root? Firstly, you gotta tell me what type of root is it? Is it a square root, a cube root, a fourth root? What is it? What tells you that? Yeah, that denominator right there tells you the type of root that you have. So if you have a 2 on the denominator, that means you're dealing with a square root. What's gonna go on the inside of our square root? 25 to what power? Yeah, the first power, because that number right there is a 1. I'm going to feel all right with this. What is 25 to the 1/2 power? Or in other words, what's the square root of 25?
5.
Which means that you don't have to change it to this to find that number. In fact, if you have a calculator, you want to plug in 25 to the 1/2 power, it will give you 5. Because it means the same thing. 25 to the 1/2 and the square root of 25 are identical. Let's try a few more. Let's try 27 to the 1/3. Can you tell me, ladies and gentlemen, what type of root does this suggest? Good. What tells you the cube? Okay, so we are going to have a radical. We know that any rational exponent is the same thing as a radical. We just have to make sure that our root is the same. Here's square root here. We can't forget the 3. That's a cube root. On the inside, we will have 27. And can you tell me what is the cube root of 27? What do you think? Yeah, because 3 times 3 times 3 equals 27. Right? We've dealt with these roots before. We're just now translating from here to here. By the way, you're going to get pretty good at this, to where you're going to be able to look at these things and know immediately, oh, that's 5. That's the square root of 25. Oh, that's 3. That's the cube root of 3. So you'll get pretty good at that. Can you do it with just a variable without some numbers? Let's see if we can translate that. Ladies and gentlemen, what type of root am I dealing with? What type?
Oh.
Fifth root? Yeah. Flipped around in your head, didn't it? Yeah, we got a fifth root here. That's all right. So we'll still have a radical. The denominator simply tells you what type of root you have. What's going to go on the inside of our root? X. Yeah. X to what power? So you can leave it just like that. That's a fifth root of x. There's no way we can simplify that right now. There's no number, so we can't say like here was a 5, here was a 3. We can't do that. Let's try a couple more. Don't answer this question out loud. I want you to think of it, okay? Now, of course, we're getting pretty good at this. You know, that's going to be 5, and that's going to be 3, and this is the fifth root of x. I want you to think of, don't answer, because I'm going to tell you the answer in a second. I want you to think of if this is possible or not. Don't say it loud. Just think. I see a lot of. Now here's the deal. A lot of people are thinking no right now because you have a negative, and what type of root is that? And what you know is that you can't have a negative inside of the square root. Imagine that with me if you understand that, for sure. But here's what you need to understand. When you're dealing with exponents, if you have something like this, -4 to the 3rd power, what this means, actually, you know what, let me make it to the 4th power. 4th power there. What -4 to the 4th power means is the opposite of 4 to the 4th. What I mean by that, this does not equal -4 times -4 times -4 times -4. That's not the same thing. What this actually equals is, here I'm trying to make it so you can really understand it. Think of your order of operations. What comes first, multiplication or exponents? Hopefully exponents come before multiplication, right? PEMDAS. So if we have order of operations, it says you're supposed to do your exponents before you do any multiplication. So what this actually can be written as, pay attention up here, you could write this as -1 times 4 to the 4th. Does that make sense to you? That is the same thing. And so what this means is -1 times 4 times 4 times 4 times 4. Or in other words, negative whatever 4 times 4 times 4 times 4 is. -4 to the 4th. 64 times 4 is 256. -256. So that even though you have a -4 to the 4th power, you're still getting a negative. Are you guys okay with this? Here's what I'm trying to say. Unless your negative is in parentheses, it is not being applied towards that exponent. Are you with me? So in this case, is this -25 going to be inside of the square root, or is it going to be outside of the square root? It's going to be outside, yeah. How I would show it inside is if I had this. Watch on the board. If I had that, then it would be inside the radical. Are you with me? If I don't have that, very important that you get this, by the way. If I don't have that, that says a square root of 25. This is the opposite of the square root of 25. That's what that is. Is that possible? That is definitely possible. Do you see the difference here? Okay, so that negative, if it's not in parentheses, it will not be inside of the radical. If it is in parentheses, then it will be. This one is actually equal to how much? Yeah, let's try to do more with that in mind. -27y to the 6th, all to the 1/3 power. To the 1/3 power. Firstly, I want you to identify if we have a root here. Do we have a root? A radical? What tells you I'm going to have a radical here? What type of exponent do we have? Okay, good. So anytime you have a fraction exponent, it means a radical, for sure. What type of a radical do we have? What type of root? Cube root, all right. And is the negative going to be inside the cube root or not? Inside or not? Yeah, why? Yeah, I want you to notice the difference. Here, there's no parentheses, it's outside. But use your order operations, that idea. Exponents come before multiplication. This is being multiplied by -1. Here, because it's in the parentheses, this says, oh, okay, I have the cube root, sure. But since it's all connected with those parentheses, that's going to be inside of my radical. Raise your hand if you feel okay with that one. Okay, I'll show you how to simplify those in a little bit. We're not going to quite go through that. Well, I guess we could actually. We could do that now. Let's simplify that. Do you remember how to simplify those from the very first section we did in this chapter? I hope so. Do we know how to do the cube root of -27? Sure. How would the cube root of y to the 6? Remember how to do that? There's two methods. You would write this as something to the 3rd power and cross this out, or you write this as many 3rd powers as you can. I'm going to do that method. So here you go, okay, cube root of -27. I'm going to leave that for just a second because I know I can take that cube root. And instead of y to the 6th, I'll do y to the 3rd, y to the 3rd. Why am I doing y to the third power? Why is that? Okay, so I want to match the power with the type of root that I have. So here we'll say, what's the cube root of negative 27, ladies and gentlemen? Good. What's the cube root of y cubed? Those are gone, right? I just have what left? Okay, so with both of them, I'm going to have y to the second. Absolutely. Yeah, this is going to give me a single y. This is going to give me a single y. So this all together, you guys are right, negative 3y squared. Absolutely. You guys remember that from before, actually before our test, wasn't it? All that. Let me show you one more thing. I'll give you something to do on your own, then we'll move on. Seven x to the 1/5. Now this one I got a lot of people on right off the bat because a lot of you were thinking, oh, this isn't possible because you thought the negative went with the exponent. I want you to look at this. I want you to look at this real careful, okay? The 1/5. Is the 1/5 above the 7, above the x, or above both of them? Just the x. Do you see how that 1/5 is just above the x? It's actually not 7 to the 1/5. If I wanted to show 7 to the 1/5, 7 and x to the 1/5, here's how I do it. I want you to see the difference here. If I want to show both of them, what would I need to put? Very similar to this negative idea. Notice how if I want to include the negative, I've got to have it in parentheses. If I don't want to include the negative, I don't have parentheses. If I want to include the number, I've got to have parentheses. If I don't, then I don't. So on this example, is the 7 going to be inside of our root or not? What do you think?
No, it's outside.
It's outside. Yeah. What this says right here is 7 times x to the 1/5. You with me? It's like the negative 1. 7 times x to the 1/5. Use your order of operations and think about this. This says I'm doing 7 times the 5th root of x. That's 7 times the 5th root of x. The 7 is not inside the radical because it's not in the parentheses. Folks, are you okay on that one? Are you sure?
Yeah.
Okay. Do you see the difference between this one and this one? This is still 7 times x, but all of that's to the 1/5 power. So this says, all right, I do have a 5th root, and everything in the parentheses is going to be my radicand, what's on the inside. So again, if it's in parentheses, yes, it goes inside of your radical. If it's not in parentheses, it doesn't. Raise your hand if you all right with this so far. Give you a left side. You guys okay with this? All right. Try a few on your own, okay? See if you can manage these. There you go. So translating these things into radicals, and then we're trying to simplify them, if we can. see if these are right. So x to the 1/4. We need to notice what type of roots these are, then be able to write this appropriately as the type of radical that it is. So what type of root do we have if I have x to the 1/4? I know it is a root because I got a fraction. What type of root? Yeah, the denominator is going to tell you the type of root that we have. So here we have a 4th root for sure. You can't forget about that 4. That tells you the type of root, right? You don't want to write square roots all the time. They're not all square roots. What is our radicand here? X to the what power? First power. Okay. You don't get the 4th root of x. Awesome. Next one, we got -9 to the 1/2. What type of root do we have? Square root. So I'm just going to write the radical without any indices because that implies a square root. One question, is the negative going to go on the inside of our square root or? Okay, so this is very much like saying this is -1 times 9 to the 1/2. Negative square root of 9. That's something that we can do. We can do the negative square root of 9. How much is that? Okay, so simplify it if you can. Okay, -3. How many people are 2 for 2 so far? Good for you. That's fantastic. Okay, next up, we have 81 x to the 8th, all to the 1/4 power. What type of root do we have here, ladies and gentlemen? 4th root. Okay, so I know that I'm writing at least a 4 for the radical. Now the 81, is the 81 going to be on the inside of our radical or the outside of our radical? Definitely, it's in the parentheses. So we got 81 x to the 8th. We have the 4th root of 81 x to the 8th. Let's try to simplify that. Can you think of the 4th root of 81? Something times itself 4 times, it gives you 81. Yeah, you think of maybe the square root and then do it one more time. So the square root of 81 is 9. The 4th root, split those up, you get 3. I'll leave that for just a second. We'll do the 4th root of 81 times, and I'm going to write x to the 8th. You can choose to do this 2 ways. Either as something to the 4th power, that would be x squared to the 4th power and cross out those fourths, or you write x to the 4th times x to the 4th. Either way you want to do that. As many x to the 4th as we can and still make up x to the 8th. So we have the 4th root of 81, y'all told me that was 3. This gives you 1x. This gives you another x, so we have x squared. Did you get that one? Good, okay. Last one, we have 5y to the 1/3. What type of root? Third root, okay, cool. So I know we're drawing a 3rd root. On the inside of our cube root, what do we have? Well, what happened to the 5? Okay, so we don't have the same situation here. Here the 81 was inside of our root because it was in the parentheses. If it's not in that parentheses, this exponent is really only being applied towards this y. It's not actually going to the 5 as well. There's no distribution of exponents like that if there's no parentheses. Here we can because, well, it's all to the 1/4 power. Here it is not. So we have the 5 up front, the y as our radicand, and that's our answer. We can't do anything more than that. How many will feel pretty good about this so far? Good. Now, what would happen if on the inside of our radical, we didn't just have a power 1? I kind of previewed this a little while ago, but what if we had an nth root of a? This is exactly how we started our lesson today, but instead of just having a little 1 here, we had another power like m. Let me draw that bigger so you can read that a little better. An nth root of a to the m power now. Well, here's what we've learned so far. We know that whatever's on the inside of our radical is going to be our base. So we're still going to have an a. But before, when we had like x to the 1/4, the denominator told us the type of root that we have. So in our case, what's our denominator here? So we're still going to have something over n. The root is always your denominator. Root, 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 root. Every time that told us the root. That's how we found it. Only this time, instead of having a numerator of 1, what do you think we're going to have? And just m, whatever the power is. Here, in every case, our power was 1. That's why we just wrote x to the 1st, 9 to the 1st. This was all to the 1st. Everything was to the 1st power. This was y to the 1st power. If I have another number besides a 1 up there, like an m, we just write a to the m over n. So it's power over root. You guys got to get that in your head. How we write radicals is power over root. Power over root. Whatever the power is, over whatever the root is. Now, if you're still okay with this. All right, good. You want to see why? Of course you do. Answer's always yes for that one. You want to see why?
Yes.
We're so excited at 7:25 in the morning to learn about why this is the way it is. Well, I can show you. You just have to trust me on one little piece of information. If we talk about this, the nth root of a to the m, you're going to have to believe me that it doesn't matter when I take this to the power. I can take it to the power and then find the root, or take the root and then find the power. So you're going to have to trust me on this one little step, but then everything else falls into place. You need to trust me that this is the same thing as this. Do you trust me? Well, it is. Well, it is. And the reason why that is the way it is because multiplication of exponents. When you take a power to a power. You do that. Well, here's the deal. We already knew how to deal with this, the nth root of a. This inside part was a to the 1 over n, right? This is this. Do you guys see it? And then to the nth power. Now, we kind of talked about this very briefly, but what happens when you have an exponent raised to an exponent? Do you add, subtract, multiply, divide? What do you do? Now, we should know those exponent rules, right? When you have an exponent raised to an exponent, you multiply them. And so here, we go, oh, okay, well, this is a to the 1 over n times m. Or in other words, m over 1. We can change m to m over 1, and those are fractions. If you have 1 over n times m over 1, we know how to multiply fractions. We go straight across. 1 times m is m. n times 1 is n, and that proves that this equals that. Can you follow it?
Yep.
Okay, so that's just a little proof. The only thing you have to believe is that step right there. Everything else kind of falls into place. Let's see if we can do some examples. It's going to be very, very similar to what we just did over here, okay? Very similar. So let's do the cube root of 2 to the 5th. Can you write that as a fractional exponent? Can you write that as a, I'm sorry, can you, as a fractional exponent? What is our numerator going to be in this case? Good. It's going to be the powers or numerator. What's the type of root that we have? So what's our denominator? Q. So this is going to be 2 to what power? Two to the 5. You ever think you'd see something like that? 2 to the 5/3. What the heck? What does that mean? 2 to the 5/3. It means take a cube root after you take 2 to the 5th power. That's what that means. Can you go the other way? Can we do nine to the 3/2? Can we do 9 to the 3/2? Ladies and gentlemen, what type of root do I have here? A square root. Why square root? Okay, so the denominator, this bottom number, that denominator is going to tell you what type of root you have every single time. So in our case, we are going to have a 9, but that's going to be a square root. Now, do we leave 9 to the first power like I have it right here? What power is it going to be? Okay. Can you simplify that? What this says is take 9 to the 3rd power. How much is 9 to the 3rd power? 9 times 9 times 9, right? Way more than 200. It's going to be 81 times 9. So should end in 9. Yeah, 729. Okay, 729. You got it? Easy. Double check that math, by the way. Is that right? Okay, and you all know the square root of 729, don't you? Of course you do. Come on. You know the square root of 729? Oh my goodness. Yeah, it's 27. How do you not know that off the top of your head? Would you like an easier way to do this?
Yeah.
Did you believe me on this step? I want to show you something. Right here, we did this the hard way. The hard way was make a really big number first, and then try to find the square root of it. You with me? That's the hard way. Here's an easier way. If you trusted me on this step, watch what you could do. Instead of having the square root of 9 cubed, I told you that this is the same thing as the square root of 9 cubed. Do you see that I just moved the 3 to the outside? Now watch, I'll bet you all can do this problem very simply. Can you tell me what's the square root of 9? Oh, everyone answered. Okay. This is 3. What's 3 to the third? Was that a lot easier? Okay, so maybe a shortcut, that's not even a shortcut, you're just doing one step that I told you was true. If you do that step and move the power to the outside, if you have to do these in your head, if you've got to do them in your head, the calculator will do this for you, no problem. But if you have to do in your head, do the root before the power if you can. You with me on that? Do you see why? You don't want to deal with big numbers, right? Deal with small numbers first. Well, let's try a few more. Ultimately, I want you to be able to write the radicals very well, and then after that, I'd like to see you simplify them. But first step, you got to be able to write these correctly. So, everybody, what is the type of root that I have in this problem? Fourth root, great. Is the negative going to go inside the fourth root or outside the fourth root? Good. And do I have any power inside that root? Okay. So, firstly, I want to see you write it correctly like this. We definitely have a fourth root. Don't forget about that 4. We've got a negative outside because it's not in any parentheses. We have a 256 to the third power and the inside of the root. Nod your head if you're okay on getting that far. Next, try to simplify it. This is step 1. I want to see that you're able to do that because sometimes we're doing variables. We can't do this process very well. So sometimes we're not going to be able to do that. In this case, we will. But firstly, write it this way. Just make sure that you can. After that, do we want to take 256 to the third power first, or should we find the fourth root of 256? You take 256 to the third power, that's insane. That's a really, really big number. Right? That's huge. Instead, you could think of it as negative fourth root of 256 to the third power like that. Take the fourth root first. Now, maybe the fourth root of 256 isn't popping right into your head, but it does exist. Say no? Well, popped into your head. Popped in my head too. It did. Popped right in there. I promise. Yeah, it is. It's a 4. So this would be negative 4 to the third. Negative 4 to the third. What is negative 4 to the third power? Well, we'd say negative. How much is 4 to the third? That's 4 times 4 times 4, right? 4 times 4 is 16 times 4 gives you 64. This is negative 64. So step 1, write the radical appropriately. Step 2, try to simplify it. Let's do a few more of these things. Negative 32 to the 2/5. We're going to We're kind of quickly through this because we should have the root down at this point. What type of root do we have, folks? Good, so I'm going to have a fifth root. Is the negative inside or outside of the root, please? Inside, so negative 32. In fact, do I have a power? Second power. Now, because this was in parentheses, I want you to watch up here on the board. Please watch. I'm not just going to put a 2 there. Right there, that 2 would not be applied to negative 32. It would just be 32 and you would take the negative. Are you with me on that? Because this had a parentheses, it really is a parentheses like that. That changes the problem a little bit. This is going to make whatever you have a positive number. Are you with me? That's what that does. So you need that parentheses. If you have one here, you also have one there, Najee, if you're with me. Okay, good deal. Now, we could square negative 32 and then take a fifth root, or you take a fifth root and then square whatever you get out of that. I'm going to choose to take the root first. So if I take the root first, what I'm doing is a fifth root of negative 32, and then squaring it. Can you tell me what's the fifth root of negative 32? Negative 2, okay. Negative 2, and then I'm squaring that number. Remember, I'm doing this part first, I'm doing the fifth root first, and then I'm squaring it to negative 2 squared, folks. That's 4. Let's try a couple more together. Maybe one on your own. Then we'll move on to some negative exponents. Look at what happens there. And after that, we'll talk about some exponent rules to refresh your memory a little bit. Okay, you knew this was coming, right? We're dealing with fractional exponents. I want a fraction to a fraction. You're crazy, Leonard. Come on, what are you doing? A fraction to a fractional exponent? I didn't know this was math class. Come on, it's only 7:35. My goodness. Yeah, what about a fraction to a fractional exponent? My goodness gracious. Well, what we know about fractions is we take the top to that exponent and the bottom to the exponent, the numerator to that power and the denominator to that power, and we solve the right thing. So you could go about and you could write this as what type of root? A square root of 1/4 to the third. That's appropriate. That's appropriate. Well, what that means is that you have a square root of 1/4 to the third. That's okay too, right? Can you take the square root of 1/4? How much is it? Okay. So this process still works with fractions. No big deal. We're going to have 1/2, then take that to the third power. We can do 1/2 to the third power. Take a numerator to the third, take a denominator to the third. What's that fraction? 1/8. That's it. So even though we have some fractions up here, no big deal. The same process works. We still know it's power over root. Whatever root we have, this is going to be on the denominator. Whatever power we need is going to be on the numerator. Write it out appropriately, and then use what you know to simplify that. Okay, one more before I let you go and do one on your own. Let's say we have two x plus 1 to the 2/7. 2x plus 1 to the 2/7 power. Ladies and gentlemen, what type of root do I have here? And it's all in parentheses, so everything's going to be on the inside of that 7th root. What is going to be on the inside of that 7th root? word associated with that? Parentheses, because, well, this was in parentheses, and it's being squared. So I can't just do this. That doesn't make sense, right? That's just squaring the 1. What I want to show is that the whole thing is being squared. Let's on that thing. You're done. You can't simplify this one. It's not like the other ones. I mean, if I say, okay, find me the 7th root of 2x plus 1, you're going to get a lot. Well, what's x? Well, no. So we can't do anything with that. Right? It's not like the numbers. Numbers, yeah, sure. We can just simplify those down. Once you get the variables, really there's only a select few things we can do, which is kind of nice, I guess, that you're done at this point. Raise your hand if you feel okay with what we talked about so far. Good deal. I want you to try one of these on your own. Let's do negative 81 to the 3/4. Like that. Negative 81 to the 3/4. Oh my. Did you find the root? What type of root? Good. Is the negative inside or outside the 4th root? You know, that's probably a good thing, because if you noticed it, if the negative was inside the 4th root, there'll be a problem, right? You can't have a negative 4th root. Inside we have our 81, no negative, negatives on the outside, but that's to the 3rd power. Now, you can do this 2 ways. You can either use your calculator, find 81 to the 3rd power, and then take the 4th root, that's fine. Or you can do the 4th root first, and then take it to the 3rd power, and that's the way we do this in our head. You deal with smaller numbers. You make it smaller before you make it bigger. You make it bigger before you make it smaller, that's harder. So we'll still have the negative, we'll do the 4th root of 81. What's the 4th root of 81? So we have 3 to the 3rd power. Remember, we're taking the 4th root first, that's the 3. We still have the 3rd power. Is the negative being taken to the 3rd power, or just 3? Okay, now in this case it really doesn't matter, right? Because we have the 3rd power. So if you did negative 3 times negative 3 times negative 3, it's going to work out the same as negative 3 times 3 times 3. But I want you to understand the whole process. So this is negative 27, and you're done. How many of you got negative 27? Good, including the negative, right? Perfect. That's fantastic.
So you put that there,
Which one?
the negative 4, no, the top one. Yeah.
You could have done this. I actually didn't show this step. I didn't show that step. But that's what we're actually doing. Okay. Have we dealt with negative exponents in this class? We did briefly, I think. Remember I gave you those problems where it was like complex fractions? We had like x to the negative 1, or 3y to the negative 2, and you did some crazy stuff with it, and it was like a 10-step problem. You remember those? Those are super fun, right? Obviously. Yeah. Well, we can still deal with negative exponents even if we have some rational exponents. So negative fractional exponents, let's do it. If you remember, a to the negative 1 was the same thing as 1 over a. Do you remember that? How when we have a negative exponent, the way we change it to a positive is just put it on the denominator of fraction, or essentially change the position where it's at. If it's negative on the numerator, which it is here, this is like a to the negative 1 over 1, we move this to the denominator. That's what we would do. We spend a lot of time doing that. The same thing happens if I have a to the negative m over n. If I have negative m over n, what that says is I have a negative exponent. Let me be real clear here. This negative has nothing to do with the sign of the number. Nothing to do with that. This answer does not have to be a negative when you're done. That's going to be okay with that. This doesn't have to do with the sign of the number. This just says that this is in the incorrect position. This is on the numerator when it should be on the denominator. Okay, if you want to make it positive. So what this says is, all right, if I want to change my exponent to a positive, I'm going to have to move this from the numerator like it's on to the denominator. I don't flip anything around. I don't change the exponent. I'm changing where that expression is. I'm changing where a to the m over n is. Don't flip the fraction around. That's not the thing. We're just changing the sign of that exponent by moving it from the numerator to a denominator. You okay with that? Very, very similar to this idea. So make a little note here. This does not affect the sign of the number. Just the sign of the exponent. Okay, let's try a few examples. Let's do 3 to the negative 2. If I want to change 3 to the negative 2 into a positive exponent, what do I have to write? Okay, good. So I'm changing, this is like a denominator, or this is like a numerator right now, like 3 to the negative 2 over 1. So if I'm going to make this into a fraction where this is a positive exponent, I'm going to move this from the top, our numerator, to our denominator. So that would be 3 to the, is it still going to be negative 2? No, positive 2, okay. Did it change the sign of my number? No. It's just my exponent, but what's going to be on the top of my fraction? 1. By this rule, move it to the bottom of the fraction, change the sign of your exponent. How about that? How about 9 to the negative 1/2? 9 to the negative 1/2. Can we write that as a positive exponent? Firstly, what's going to be on the numerator of our fraction here, ladies and gentlemen? Good. Are you guys all still with me on this? Why we have a 1 there? What's on the denominator of our fraction? Do we still have the 9? Okay, we're going to have a positive 1/2. We're going to change the exponent to a positive. Can you deal with 9 to the 1/2? What's 9 to the 1/2 mean? Okay, so yeah, the 1 is going to be there. We're good at this, right? This says what type of root? Of 9 to the, what is the square root of 9 to the first? 3. You can change it to a square root if you want to, or if you're getting good at this, just go right to the same thing as 1/3. Because this right here is the square root of 9 to the first. So a few more examples and we'll call it a day. Okay, 27 to the negative 2/3. First thing we're going to do is make that exponent into a positive. I want you to do that right now on your paper. Make the exponent into a positive, write what you need to do. We should get a fraction somehow. What's on the top of our fraction, folks? Good. What's on the bottom of our fraction, please? Good. All right. Did you make that far? Now once we've done that, we have the positive exponent. Now we can use what we just learned and simplify the thing. You can't really simplify here. It doesn't really work. We don't know how to deal with a negative version of a root. What that means is, okay, just move it to the denominator of fraction. That's really what it means. So here, can you simplify 27 to the 2/3? What type of root do you have? Cube root. What type of power do you have? So what this means is 1 over a cube root of 27 squared. We've already done that. That's what we just learned. So you could square the 27 first, or you could cube root the 27 and then square. I'm going to choose to do that way. Can you think of on your own what that, don't say out loud, just think of on your own what that's going to be. What do you think it's going to be? 3 cubed? How much? 9. Yeah, it's going to be, the cube root of 27 is 3, then you square it, you get a 9, now you're going to be still okay with that. So we're going to get 1/9. It's kind of interesting that this whole ugly thing is actually equal to 1/9, isn't it? It's kind of weird. Much easier to write 1/9. Why don't we just do that?
Make it that complicated.
It is, right? It's complicated. The problem is you get this a lot. You get this type of stuff a lot in math. We have to know how to simplify it. All right, let's do one more. Yes, let's. Here's what I need you to know. I'm going to show you this example for one really good reason. What am I trying to change? Am I trying to change the first negative or the second negative? Will I ever be able to change the first negative? Not by moving it. So when you do this, you go, okay, yeah, I have 1 or -1. I don't really care what you put there. But on the denominator, I have to have a negative somewhere. I'm going to carry with this 256. I have negative 256 to the positive 3/4. I need you to notice that, yes, the sign of the exponent changed. That's what we're doing. The sign of the number did not change. It doesn't affect the sign of the number. Now, we've already done this problem. In fact, it was on the board. I just erased it. Does this negative go inside of the 4th root that we're going to have or outside the 4th root? So we're going to have 1 over negative 4th root of 256 to the 3rd. We've actually already done this problem. The 4th root of 256, do you remember what it was? What is it, 4th root of 256? 4. And then we take the cube of that, we get 64. So this is 1 over negative 64. Or it doesn't really matter where you put that negative. You get negative 1 over 64 or negative 164. That's the idea. If I did give you something like this, negative 64 to the negative 2/3, would you be able to do it? Let's talk about it for a second. First thing you do is write this as 1 over what?
1 over 64.
Would it still be negative? Is this negative ever going to change? Is this negative going to be inside the cube root that you're going to write eventually? Okay, it would be inside. How many feel pretty good with what we talked about so far? Good. So last time we learned that every single root that we have, second root or square root, cube root, 4th root, everything about those can be written as rational or fractional exponents. We're going to learn today that those fractional or rational exponents can be used just like regular exponents we've been dealing with since your algebra classes. So we'll refresh your memory on some rules. Your exponent rules, and we'll apply to those rational exponents. First one. If I give you some, and we're going to use general terms here, not actual specific numbers, we'll deal with those later. I just want to refresh your memory on the actual rules here. If I give you some common bases that are multiplied together, such as x squared times x to the 4th power. If I have a to the m and a to the n power, we're multiplying those things. What do I do with the exponents? Do I add them, subtract them, multiply them, or divide them? We add them. Yeah, that's right. So if I have a to the m times a to the n, we know that's a to the m plus n. I just add those exponents. This should be a little bit of review for us. Second one, if I have, you know what, maybe I'll do an example over here. X squared times x to the 3rd is, well, x to the 5th. We just add those exponents together. If we have an expression that has an exponent in it, being raised to another exponent, such as a to the m power, and then we take all of that to the n power, do we still add those exponents together? No, we do multiply, that's right, because what this says is I have a to the m times a to the m times a to the m times a to the m, n times, and every one of those we would add those m's together, so that's repeated addition, that means multiplication. So here we'd have a to the m times n. For instance, if we have y to the fourth to the third, that's going to give us y to the 12th. This is kind of an important one for us, assuming we're a lot, well, for us, it's going to happen a lot, this situation. If I have a times b and I raise all of that to some power, raise all of that to some power. What you need to know is that across multiplication, it's not like you're distributing, you're not actually multiplying these things, but you're raising every single factor in there to that exponent. So if I have a times b all to the m power, then I know this is equivalent to a to the m times b to the m. For instance, if I have y, sorry, let's make it xy. If I have xy to the third, that means I'm going to have x to the third times y to the third. It goes to both of them. Hey, by the way, is this true for addition? For instance, if I do a plus b to the n, is that the same as a to the n plus b to the n? Is that okay? You think so? Okay. Let's make it even easier. How much is this? 5 squared? How much is this? How much is this? Is it the same?
Oh, no.
Does this work? Does this work? Never do that. Never do that. Okay? You can't distribute, or if you want to say distribute. You can't take an exponent across addition. It doesn't work. It's proved to you, right? There's one example that does not work. So this does not work. So are you ever going to do this?
No.
Can you do this?
Yes.
Yeah. It's a different story, okay? So when you have this product in here, that's fine. Both those factors get raised to the same exponent. However, if I have any addition or subtraction, and I have that term, or those two terms being added together, and I raise that to the exponent, you can't just break that down. Right? For instance, right here, we have the 2 plus 3 squared. There's no way this equals 2 squared plus 3 squared. This is 25, this is only 13. There's no way they're the same. Don't you gotta be okay on that? All right, so make sure you have that down. I'm gonna erase this just so we're sticking with our rules. But if you wanna write that down, this is just one instance. Where you cannot do that.
So it's just like a formula system, right? It was just a plus b plus h and a plus b was squared.
If that was a square, sure.
Oh, okay, yeah.
If that was a fourth power,
Then it would be 4 times.
yeah, that'd be messy, right? I mean, you don't want to do that, but you could. You just can't do that. Okay, back to our rules here. If I have some fraction to an exponent, what we need to know is that just like here where we have the product and you have your product raised to the n power, if I have a fraction raised to the n power, both the numerator and the denominator get raised to that power as well. We've talked about that before in this class, so we're just going to write a to the m over b to the m. It just goes to both the numerator and denominator. Very, very similar to this one. It's just you're dealing with the quotient instead of a product. If I have a quotient where I have the common base there, a, I have a to the m power over a to the n power, if I multiplied common bases and got to add exponents, when I divide common bases, what am I going to do to those exponents? And multiplication means you're going to add those exponents. Division means you're going to subtract those exponents. And we do it like this. We do the a to the m power minus n power. M minus n. The top power minus the bottom power. I guess I could give you some examples here, huh? So for this one, if I did 3 over x to the second, that'd be the same thing as 3 to the second over x to the second, or 9 over x squared. If we wanted to do common bases, we'd do something like y to the second over y to the fifth. If I did y to the second over y to the fifth, we have common bases, we have y to the second, y to the fifth. What we do here is we'd say, this is the same thing as y to the, what comes first, 5 or the 2, if I'm going to subtract the 2? It makes a difference, doesn't it? The 2 would have to come first, it comes on the numerator there. 2 minus 5, what's our answer going to be? Y to the negative 3, okay. Say that again? That's right. So if I write that as a positive exponent, remember doing that last part of class last time with those negative exponents, we change those back to a positive. You go, okay, instead of y to the negative 3, I don't like that so much, I want to do 1 over y cubed. I'm going to move over here with the rest of our rules so you all can see them. There's only 2 more. Next one. What's anything to the 0 power? How much is that? Some people say 0, some people say 1. What is it? It's not itself. It's 1. It's 1. Anything to the 0 power is defined as 1. And lastly, a refresher. We did this last time, it's a good little note to have. Anything to the negative exponent, we can always change it to a positive exponent by doing what? So wherever it is, we change the part of the fraction it's on. If it's on the numerator and it's negative, we move it to the denominator. If it's on the denominator, we can make it positive by moving to the numerator. We just change the spot of the fraction where it is. So for instance, right here, we consider this to be on a numerator because you can write that over 1. If we want to change the a to the negative n to an a to the positive n, what we have to do is we have to write this on the denominator fraction. Remember, recall from last time that it doesn't change the sign of the number, it just changes the sign of the exponent. And we did several examples, but I'll give you another one over here. Let's see. X to the negative 4, we could write that as 1 over x to the 4. Hey, would you raise your hand if you feel okay with these rules? They should be a refresher for you, right? Should be a refresher for you. Now, what we're going to do is we're going to take these rules that we just kind of reviewed, and we're going to apply them to our rational exponents. What you need to know is that every one of these rules works exactly the same way for rational exponents as it does for whole numbers. Now, I gave you some whole number or integer exponents, but right now I'm going to give you those fraction exponents. They work the same. As long as you stick with these rules, there's only 7 of them. Most of them are very refresher. The only one that really might be a little new for you is using this those fractions, but it's the same ideas. Are you guys ready to try some examples here? Okay, let's do that. Okay, we got x to the 1/3 times x to the 1/4. Ladies and gentlemen, do we have a common base there? Do we have a common base? And they're being multiplied. So when we look at this, we're multiplying them. What situation are we most like? Rule 1 through 7. Which one are we most like, do you think? Well, number 1. I've got two things with a common base that are multiplied together, and I have some exponents up there. So what am I going to do to those exponents? Am I going to add them, subtract them, multiply them, or divide them? What do you think? For sure I'm going to add them. That's what that says, right? You know what a lot of people do? A lot of people do this. They make the mistake and they're doing this really quickly because they get the handle on it right, but then they're really not reviewing it enough, and they get to the test and they go, oh, that's x to the 1/12. Do you see how easy that is to do? If you're just thinking multiplication, your head's thinking multiplication, right? You're not thinking really the exponent rules if you're just seeing this. When you just see this, you go, oh, 1/12, yay, uptime. Well, if we do that, we're kind of missing the big picture here, right? These are exponents. And exponent rules say if I'm multiplying common bases, what I'm really doing is I'm adding those exponents together. That's what I'm really doing. Now, can you add 1/3 plus 1/4? You do. We know how to add fractions, right? This is a fraction class. We're past fraction class. That's great. So use your calculator. I don't care if you use your calculator or do it off the side. I would personally do this off the side. I just say, okay, I know I need to add 1/3 plus 1/4. That means the common denominator. Common denominator is going to be what? So we're going to multiply this by 4 over 4. This by 3 over 3. We'll get 4/12. We'll get 3/12. That's going to give us 7/12. So instead of x to the 1/3 times x to the 1/4, or x to the 1/3 plus 1/4, we actually added those and we got x to the 7/12. Are you okay with that one? Hey, by the way, could you write this as a root? Could you write that as a root? What type of root do we have? 12th root of what? X to the 7/12. So if you wanted to, if the problem asks for it, that's that root. These things are the same thing. So this actually makes that. I want you to see how this stuff actually works here. Notice that the common denominator is the root, isn't it? That is the root. Because we know that the denominator makes the root up, so when we find the common denominator, that's making a common root. This you could have written as a cube root of x, right? This you could have written as a 4th root of x. Multiply those two things together, you have to find a common root. In that case, it means a common denominator. That's why all this stuff is intertwined. It works. All right, let's move on here. Before I do, are there any questions on that example? Because this just is our start off point. Are you guys all right with that one?
So the final answer is the square root?
If it asks for the root, then yeah, that's the final answer. If it doesn't, you can definitely leave it x to the 7/12. You don't have to do this. What I'm trying to do is make you remember that this is possible. Okay, I don't want you to forget this. 9 to the 2/5 over 9 to the 12/5. Hey, let's look back at our rules. Can you tell me? What rule are we most like? 1 through 7. There's only 2 that have fractions, right? There's 4 and there's 5. The 4 would be everything raised to a power. We're not there. We're actually at number 5, where we have something raised to a power and something raised to a power. We have the common base there. You with me on that? That's 5? Okay, so what are we going to do with those exponents? Add, subtract, multiply, divide, what do you think? Definitely subtract. What we do in this case is we take our 9, we write only one 9 because we're combining the exponents. We're combining these two things by subtracting exponents. Are we going to have 12/5 minus 2/5 or 2/5 minus 12/5? Can you do 2/5 minus 12/5? That's kind of better than that problem, right? You don't even need a common denominator. It's already there for you. That's great. How much are you going to get? 2/5 minus 12/5. It's negative. Okay. Is the number negative or just an exponent? Negative 10/5. Are we done? What do we need to do? This is a fraction. Even though it's an exponent, it's still a fraction, which means that you can simplify it just like you would any other fraction. So negative 10 over 5, we know that's negative 2. We're not going to do negative 10/5. I don't want that. We say, oh, okay, that's 9 to the negative 2. Tell me another thing we can do with that. This is another rule. What rule is this? No. That's number 7. It says, okay, anything that's raised to a negative exponent, we can make that a positive exponent by putting that on the denominator of a fraction. So right here, we're going to go, all right, I want 1 over 9 squared. 1 over 9 squared. Ladies and gentlemen, how much is 9 squared? So this is 1 over 81. Gee, so we worked this all the way down. We only got 1 out of 8. Isn't that kind of interesting that this means the same thing as that? Just by using our rules and manipulating that, we get that down to 1 over 81. It's kind of cool, right? That's a whole lot easier to think about than that.
Can you go back to the original problem?
You can, but I mean, it's after you do all this, if you just look at this, there's no way to tell that that's what you started with. Why? Y to the negative 3/10 times y to the 6/10. Hey, again, what situation are we? Let's look closer at the board. What one are we? What do we look like here? Well, we're still in number 1. We've got common bases. We're multiplying. That's definitely number 1. What are you going to do with these exponents, folks? You're going to add them. Even though one's negative, that's okay. You can still add them together. That's fine. So we know we're going to have y to the negative 3/10 times y to the 6/10. I just wrote the same. since we had this common base and we're multiplying, we know we're going to add the -3/10 and the 6/10. What's great is we already have a common denominator. If you don't have a common denominator, you got to find one if you're adding fractions. That's what we did in this first example. But now that we have -3/10 plus 6/10, how much are we going to have?
3/10.
Awesome, 3/10. Okay, very good. Add those together, you get 3/10. Could you write this as a root?
Yeah.
10th root.
Good, yeah, 10th root, because that's our denominator, and the power is the numerator, so we would have that exactly. That's as far as we could go. Would you raise your hand feel okay with these ones so far? All right. We're going to try a couple more together. I'll give you several to do on your own. I'll make sure that you guys can do this. Then I'll move on and I'll show you how we can really apply this to some unique ideas. Eleven to the the 2/9 to the third power. 11 to the 2/9, all raised to the third power. What do you think about this one? What rule are we for that? Number 4? Number four would be a fraction raised to an exponent. We don't really have a fraction. We have, that's an exponent, right? And that's an exponent. Which one is that?
2.
That's number 2. That's right. This says an exponent raised to an exponent with some number or some value. We have some value. We have an exponent raised to an exponent. Did you guys see it? Yeah.
How come you don't have the third power to the base?
This one to this one?
Yeah.
You are. You are. Because what you're doing here is, this means 11 to the 2/9. This would be 11 to the 2/9 times 11 to the 2/9 times 11 to the 2/9.
Oh.
Does that make sense?
Yeah.
And when you do that, you don't multiply the 11s. They're already being multiplied. You're taking those exponents and you're making it so that you don't really have to deal with the 11s. You're dealing only with the exponents. Indirectly, you are dealing with them. Does that make sense? You are doing that. Okay, 11 to the 2/9 to the third power. What are we going to do with those exponents, folks? Definitely multiply them. Yeah, we have an exponent raised to an exponent there. Exponent raised to an exponent. So, the base doesn't really change when you're dealing with exponents. But up here for our new exponent, we'll have 2/9 times 3. We're multiplying those exponents. Here's how. Okay. How? What are we going to get? Just like you would any other fraction. For instance, this is 3/1. Could you simplify that? Sure. What simplifies out of that thing? Okay, you can get 6/9, but then you'd have to reduce that. If you simplify this, you know 3 goes into 3 one time, 3 goes into 9 3 times, and there that's going to give you the 2/3 that you would reduce that 6/9 into. To the 2/3 power, and again, we could write that as a root. This is a, what type of root, folks? Square.
Doesn't require 11 to 121.
One, but that you can't go any further with that. So either way, I don't really care. I just want to make sure you're okay on getting at least this far and understanding that this can be written like that. That's really what I care about. Are you ready to move on? Okay, we're going to start combining some of these rules together. So that we're not just doing one. Here we've just done one rule 4 times. Now we're going to start putting this all together. There's a nice looking one, huh? Yeah. Yeah. That's what you like to wake up to in the morning. That's it, right there. Nice cup of coffee and some math. Best day. That's what you're gonna do tomorrow, I bet. I don't think I'm gonna do that tomorrow. So we have 3x to the negative 2/3 to the 3rd power and then x squared. First thing we're gonna deal with is very much like order operations. You're gonna get rid of any parentheses that you see. So we're not gonna deal with this x squared until we deal with all this stuff up here. You with me on that? So let's deal with all that stuff up there. Now, going back to your rules, I want you to look at rule number 3. So look at rule number 3. On rule number 3, it says if I have some things, some terms, some factors being multiplied together inside of my parentheses and it's being raised to an exponent, each one of those factors gets raised to that exponent. Are you with me? Look, I want you to look at what I have. What I have here is a product. That's 3 times x to the negative 2/3. Are you with me? What this says to you is that each of those factors, since 3 is a factor and x to the negative 2/3 is a factor, gets raised to that power. So what happens here is we don't just get a 3 back. We don't just get a 3. Since it's being multiplied there, it says that the 3 is also getting raised to the 3rd power. Are you with me on that? So what am I going to have is instead of 3? I'm going to have 27, or 3 to the 3rd. Now, how we do 3 to the 3rd, I want you to think about this. We're not just arbitrarily raising a number to a 3rd power. Please watch carefully on the board. This is 3 to the 1st power. Are you with me? So really what you're doing, you're saying, oh, I have 3 to the 1st, 2 to the 3rd. What's 1 times 3? That's how we're getting 3 to the third. Okay, that's how we're doing it. We just say, oh, we're taking to the third power. The product of those exponents still works for us. When you have an exponent raised to an exponent, we do multiply every single time. You just need to know that this 3 to the first power is also being raised to that exponent. That's how we're getting 3 to the third. Nudge your head if you're okay with that. Okay, that's good. Now, we do have something else in there that's being raised to the exponent. We have x to the negative 2/3 to the third power. What are we going to do? Add, subtract, multiply, or divide those?
Multiply.
What do you think? What do you think? We're definitely not going to add them, right? There's no common basis. We have an exponent raised to an exponent that says we're going to multiply those things. So here, we multiplied the 1 times 3. That was just the first power. We had 3 to the third. Now we're going to add x to the negative 2/3 times 3. And of course, we're not even going to worry about that x squared so far. Okay, that's kind of a big step for a lot of people. I want you to really take a look at it. If there's questions, you need to let me know right now. Are you okay that we're going to have 3 to the third power, not just 3? Are you okay why we have 3 to the third power? Because x is 1, we're multiplying that times 3, that's how we're getting 3 to the third. Are you okay that these two things need to be multiplied, and that's what we're getting here? Yes, no? All right. Does this simplify? How much are we going to have out of that? Yeah, those 3's, those are gone. It's like 3/1. So we can simplify fractions like you were taught a long time ago. By the way, I'm going to leave this in terms of the power just so you can see this all the way down. You can write 27 if you want to. I'm just going to leave it 3 to the third for now. Just so you can see for that one step of that 3 to the third, it's still there. I'm going to change it to 27 in the next step. Hey, is there anything else that I can do? I could. There's actually options here for you. You can do 2 things. You can do 2 things. Watch on the board. Since that's a negative exponent, you could move this to the denominator of the fraction. If you did that, what you would get is 3 cubed over x squared times x squared. You see where that x squared is coming from? That's this one. That's moving to the bottom. Remember, this is multiplied, and we moved that to the denominator. It's still going to be multiplied right here. We move that to the bottom, it becomes a positive exponent. You with me on that? Then could you combine these? That's going to be x to the what? Good. We add exponents for that. That's x to the 4th. Or you could think of it like this. You have 3 to the third. To combine these exponents, ignore that for a second. That's x to the negative 2 over x to the 2. How do you combine exponents when you're dividing common bases? Subtract. You'd have x to the negative 2 minus 2. You see where the minus 2 is coming from? That's, what was that rule? Rule number, that's rule number 5, you're right. That'd be rule number 5. It says you have common bases being divided, you subtract top exponent minus bottom exponent. How much is negative 2 minus 2? 3 cubed x to the negative 4. Is it going to work out the same? Which one do we move to the denominator? Do we have to move the 3 to the third? That's a positive exponent. Leave it. This is x to the negative 4. That one would move to the denominator. This would be 3 cubed over x to the 4. This one would be 3 cubed over x to the 4. Either way, you get the same answer on that. You have options on this stuff. There's not one right way to do it. These rules, you can do them in different orders, provided you stick with the exponent rules. They're fine. It's fine. You get rid of your parentheses first, and then we combine whatever we can.
When you move x negative 2 down, you move the sign 2.
The sign of the exponent will change if you change it from a numerator to a denominator. And that's the whole idea for rule number 7. Raise your hand if you're okay with this example. Good, okay, I'm going to give you some to try. I'm going to give you some simple ones to start with, and then the last one I give you is going to be pretty nasty. You ready for it? I definitely want you to be able to do those three with no problems. These are just the basic rules for us. This next one's going to take you some time. This is the one where I need you to get to ultimately, okay? If you can do this last one I'm about to give you, you're set already as far as the test goes on this idea. Okay, this is where I need you to be problem about to go forward. You will have a problem like this one on your test. So work them out. Work them out. It's a nice set. And then it's this one. So first three, no big deal, just kind of reviewing the excellent rules. Last one, big deal. Big deal. Lots of stuff. But I think you're ready for it. I hope you're ready for it. Did you get y to the 10/3 on your paper? For the first one?
Yes.
Or cube root of y to the 10th? Add those, we get the 8 plus the 2, we have a common denominator already. We get 10/3, cube root of y to the 10th. Yes, no?
Yes.
Keep working on that one, I'm going to do another one. You get to 5 to the negative 7 over 7? Can you reduce that? 5 to negative 1, we're not going to leave that though. We don't want negative exponents up here. We're going to put this as what? 1/5 of the first, or simply 1/5? Common bases. Did you get x to the 2/9? We still add those exponents, however, one's negative. So we know that 4/9 plus negative 2/9. Addition rule says different signs subtract sign of the bigger number and we get positive 2/9. You could write this as a 9th root of x squared. I need to know how many people are 3 for 3 on those ones. Good for you, all right. If you're not, review those rules that you missed. Was it a sign error? Was it subtract, or was it multiplying instead of adding? Those are the big ones right there. Look for those. Are you okay on the first 3, folks? Are there any questions on the first 3? Okay, now the last one. That one's kind of fun, right? Lots going on here. Lots going on. We've got big fraction, we've got huge parentheses, all raised to an exponent. What we're going to do is break this down little by little. We're going to completely ignore the denominator for now. We're going to wait till we get all of this stuff simplified as much as we can, and then we're going to include the denominator there. You with me? Let's do it. So we have this large parentheses, all raised to the 4th power. Can you tell me how many things inside of my parentheses are being raised to the 4th power, or need to be? How many? 3. So not just these 2, we also have that number 3. Don't forget about that 3. So we know that this is going to give me what? Good. The reason why that is because I have 3 to the 1st power. I take an exponent to an exponent means multiply. 1 times 4 is 4. That's why we get 3 to the 4th. Now here we have x. This is a 1/4 power to the 4th power. We're taking an exponent to an exponent. You need to multiply that. So it's going to be 1/4 times 4. It helps to write this stuff out. Don't just do it all in your head. Sometimes that's more tricky. Next up, we get the y. We got all 3 things. Y to the negative 2/3. We're taking an exponent to an exponent again, which means we need to multiply. And I'm just going to put that denominator up there because we need to keep track of it. Did you make it that far? Good, all right. Let's see about those fractions now. I'm going to leave 3 to the 4th. You can put whatever that is, 81, if you'd really like to, that's fine. In fact, on your final answer, it's probably going to be 81. Let's go ahead and simplify whatever fractions we can. We have 1/4 times 4, how much is that? So we're going to have just x to the 1. X to the 1st power, we have 4/4, those simplify to give us a 1. Times y. How about negative 2/3 times 4? Negative 2/3 times 4. Negative how much? Negative 8/3. Okay. Nothing simplifies there. Remember, this is over 1. And we still have this denominator, x to the 4th, y. Okay, all right. Are we done? We still have common bases on the numerator and denominator. You need it so that if you ever have a fraction, everything's being multiplied. If you have the same bases, you can combine them. You can't leave it like this. This isn't good enough. This is about halfway done. You have one more big step to do. We're going to look for anywhere we have common bases. For instance, our x's and our y's, and we're going to combine those with our rule number 5, taking our exponents and subtracting them. So if I have common bases over each other, I subtract those exponents. Are you with me on that? Now, you could move this one to the denominator first and add those together. I gave you that option over there. Remember that one? You could do it this way. That's okay. However, for this one, they're both positive. You need to use that subtraction. And in fact, I'm going to use the subtraction here as well, just to make everything using the same rules. I'm going to do it this way. Are you all right with that? Okay, so we're going to keep going on that way. So the first thing I know is that 3 to the 4th, that's as good as I'm going to get out of all. There's only one 3. We can't combine anything else with that. But I do have those x's and those y's. This is x to the 1st power over x to the 4th power. So what I'm going to do here, I'm going to take x to the What is it? Are we going to add them or subtract them? 4 minus 1 or 1 minus 4? 1. The top one minus bottom one. Whatever this gives me, that's going to be my final answer for my x's. Right there, it's my exponent there. 1 minus 4 times y. Okay, we have negative 8/3 over y to what power is that one? Is it just going to be negative 8/3? Does that 1 do anything? We're subtracting it, yeah. So it's y to the first power. So when you're doing this, you go, okay, I know that my column bases are one's a numerator, one's a denominator. I know to combine those, I subtract exponents. Top exponent minus the bottom exponent. So it's not just negative 8/3, it's negative 8/3 minus 1. Raise your hand if you're okay seeing all that stuff. You guys in the middle of the art with that? Yeah. Let's keep going. 3 to the 4th, I'm going to leave it. X2 to 1 minus 4, how much do we get out of that? Times y2. Oh, negative 8/3 minus 1. Negative 8/3 minus 1 is the same thing as negative 8/3 minus 3/3. Find the common denominator. Negative 8/3 minus 3/3 is the same thing as negative 11 over 3. Negative 11/3. This is a fraction class, right? We're beyond this, so I'm not going to really spend a whole lot of time doing these basic fractions. You need to be able to do that part on your own. Yeah? You need to be able to do that part. So take our fractions, common denominator, subtract them. We get y to the negative 11/3. Are we going to leave it like that? Yep. Rule number 7 says I'm not going to leave any negative exponents. Negative numbers, sure, but negative exponents, no. So how many things do we need to move down to the denominator? 1, 2, or 3? The 3 to the 3rd, we're going to leave that. I'm sorry, 3 to the 4th. We're going to leave the 3 to the 4th. But the negative exponent, we're going to drop that to the denominator, thereby changing that to a positive. The y to the negative 11/3, we're going to drop that to the denominator, and making that a positive exponent. And that, folks, is as good as we can do. 3 to the 4th. Over x to the 3rd, y to the 11/3. Positive exponents all in the right places. We've combined everything we possibly can. You're done. I don't need to see the radicals. I just wanted to make sure before you do that they existed still. But that's as good as we can get. How many people enjoyed that problem? Don't raise your hands. You're lying if you didn't enjoy that. Takes a lot of steps, but did you understand it?
How many of these kind of problems are you on?
Oh, no more than 16. 17 plus. I don't know, 1 or 2. There's a lot more material that we have to cover. Besides just this. Can you follow it though? Of course, that took us a while, but when you get the handle on these rules, stick with them. Have them in front of you when you're doing your homework. But another thing, when you're doing your homework, you need to progress past looking notes, doing a problem, looking notes, doing a problem, looking notes, doing a problem. If you're doing that, when you get to the test, you don't know well enough. Okay, if you're having to refer to your notes every time you do a math problem, you don't know it well enough. Because you need to go back and make sure that you can do a couple with your notes. That's great. Look at the book for a couple examples. That's fine. Then come away and see if you can do the problems by yourself. Okay, that way you know that you do these problems. So make sure you're trying that on your homework. Now, let's extend the concept just a little bit further. We should be okay on all this stuff. However, there's a couple more things that we need to be able to do with this. Namely, what can I do with that thing? Oh my gosh. It's not just multiply anymore, I have some subtraction. Well, I'm going to make this kind of a similar problem over here. essentially I just dropped the denominators. I made this similar problem. Now I want you to ignore this for a second. Just ignore this one. Look at this one. Could you do that? How would you do this? What's that called when you like? Not factor. Factor is the opposite of what we're about to do. We're going to distribute. Remember how to distribute? I hope you do. Well, you should. If you're in this class, you know it. I mean, you've done this a long time. Distribute says you take this outside one, you multiply it times each inside one, right? So can you tell me what is x to the third times x? X to the, how are you getting x to the fourth? Okay, this is x to the first power. So how I do this, I do, x cubed times x minus x cubed times x cubed. Are you seeing where All these things are coming from. But I tried to do, this is distribution. You need to know distribution at least to be here. You need to know that. Now, if we have x to the third and x to the first, we know that we add those common bases, the exponents of those common bases, we get x to the fourth minus, what is that, x to the sixth or x to the ninth? X to the sixth or x to the ninth. We're multiplying common bases. Don't let your mind trick you and go, oh, this is 9. Common bases, what do you do with those exponents, folks? You're going to get x to the sixth. You okay with that? We can use this idea of distribution even when we have rational exponents. It's fine. It's the same exact thing. When we took x to the third times each of these two, we're going to take x to the 3/4 times each of these two. However, instead of just doing this in your head, you could probably, most of you could probably just go from here to here, right? I hope so. I mean, you just x to the 4th, x to the 6th, no problem. I'm going to have you write these ones out like this so that you can see the rules. You see, the problem with distribution with rationals is people a lot of the time, they love to do this. They love to go, oh, x to the 3/16. I'm done. Because you think multiplication, we're not multiplying. Okay, we're adding those exponents because we're multiplying common bases. So what I'd like to see from you, sure, we're doing x to the 3/4 times x to the 1/4. We're taking the first outside factor times each inside term. Are you seeing where this is coming from? Okay, then we're going to have a minus, and we're going to do x to the 3/4 times x to the 3rd. Can you tell me, if you ignore this, does that make sense? Familiar? Is that familiar? We started the section. those exponents.
Or,
Yeah, exactly. You're going to add those together. You're going to add these together. Don't rush through this stuff, otherwise you might make a mistake. Go slowly, think about the rules, do them deliberately. You have x to the 4/4 or x to the first minus x to the 3/4 plus 3, that's 3/4 plus 12/4, that's going to be 15/4. Add those together, you'll get 15/4 out of that. Check my math and make sure I did that right, by the way. So x to the first x to the 15/4. By the way, can you combine x to the first and x to the, this is where we're stopped today, can you combine x to the first minus x to the 15/4? Can I subtract those? Let me ask you a different question, similar question. Does that equal x to the first? I need to know that. What do you think? Wow. I have some stumped looks out there. It's a good thing I asked about this. Can you combine this?
No.
Why not?
No.
Can you combine this? Can you combine this? Can you combine that? Can you combine that? Like terms have the same variable, the same exponent. If you do not have like terms, you cannot combine them. Do you have like terms here? Are they the same variable? Yes. To the same exponent? No. You cannot combine that. Unless you have exactly the same variable, the same exponent, you can't add or subtract. Multiply, divide, sure, because you know you can multiply x cubed times x squared, right? That's fine. That's x to the 5th power. No problem. But as soon as you start subtracting or adding, you cannot combine those like terms. You have to really understand what I just talked about. Okay, start there next time. And we have an example like this. We're realizing that this is really, really similar to something along these lines. If we wanted to consider this to something we've already done before in this class, we do something like this. Now, how would you go about simplifying that problem, getting rid of the parentheses? What's that process called?
Foil.
FOIL. Okay, FOIL is a very simplified way to say this other word. Distribute. We're going to distribute. Just like we did in the last couple examples that we did last time in class, we're going to distribute this. Now, you tell me, what do you do when you distribute? What's the process? Okay, multiply. No, you're right. What's the first two things we're going to multiply? So we do the x to the 4th times x to the 4th. Now, in this process, when you distribute like stuff like this, you probably do it in your head, right? You just go x to the 4th times x to the 4th, and you're going to give me x to the 16th, right? Really? Well, why not x to the 16th? Okay, now we catch that in our heads usually when we do our distribution, but really in this problem, a lot of people don't catch that. And a lot of people would give me like 1/16 out of that line, and they're thinking, oh, we multiply. What I'd like you to do is, instead of doing these problems completely in your head, take the extra 5 seconds and write out one extra step. This is going to let you see the excellent rules that we've been practicing last time. Trust me on this one. If you try to do a lot of this stuff in your head, sometimes you're going to make some mistakes. If you write it out, a lot of times you catch those mistakes. Not going to do it. So instead of doing this directly through my head, we're going to go, okay, I know I'm doing x to the 4th times x to the 4th. That's here. I know I'm going to be doing, we have a positive times, we're going to consider that a negative, because you could write this as plus a negative. minus 7 times x to the 4th plus 1 x to the 4th. And lastly, we'll have our minus 7. You still okay on that one? Then we do the math. Then we look at the exponent rules. We go, okay, if we have x to the 4th times x to the 4th, we know that when we're multiplying common bases, we're not multiplying exponents. That would be an exponent raised to an exponent. We're actually adding those things. So instead of x to the 16th, we're getting what here, folks? You gotta play along. You gotta play along. And you gotta be here with it. Minus. Now, the last thing that I taught you is that we really can't combine any like terms unless we have, we can't combine terms unless you have exactly the same variable raised to exactly the same exponent. So in our case, I asked, could we add together something like x to the 8th and x to the 4th? Are those combinable? However, we do have a couple things that we can combine. What could we combine here?
X to the 4th.
Good. What is x to the 8th? This one?
No, I'm sorry, never mind. Yeah.
What are these ones?
X to the 4th, 7x to the 4th, and x to the 4th.
Now listen, you gotta do this for me. If you're gonna combine these two things here, which they are like terms of the same variable raised to the same power, you got x to the 8th minus, do me a favor, combine these like terms correctly. If I combine these like terms, I'm just looking at the coefficients basically. I have minus 7 and plus 1. I'm gonna get negative 6 out of that. Am I gonna get x to the 4th or x to the 8th?
X to the 4th.
You sure?
Yeah, because you're adding that multiplying.
Okay, so if I combine like terms, I want you to realize something here. Some of you guys really aren't getting this yet. You're going to see a crossover in a second, though, and then you're going to get it. If you don't have like terms here, which means you couldn't combine them, right? By combining these terms, it doesn't magically make this like term, because then you would have been able to combine these, right? So when you're combining like terms, don't change the power. The power only changes if you're multiplying things. That's when the power changes. With your combining like terms, the power doesn't change. So we are going to get still x to the 4th minus 7. There's no like terms you're done on that problem, or you kind of feel all right with that. Now let's draw some comparisons and do that problem. First thing we do, if we were to FOIL this, we're going to do the same thing here. Just don't do the stuff in your head. Go ahead and actually write out this step that's going to help you with these fractional exponents. The first thing we're going to multiply is x to the 1/4 times x to the 1/4. We're going to write it out. We're going to write it out. We're not going to do that step in our head yet. The next thing we're going to do, you're going to notice I use the same exact numbers for a reason. That way we can just look exactly the same process of these things. X to the 1/4 times minus 7, you're going to get minus 7x to the 1/4, just like you're distributing like normal. Then we get our plus x to the 1/4, and lastly we're going to get our minus 7 at the very end. Do you guys see the similarity between this problem and this problem? Okay. Now, since we've written this out, we can do this process step by step. And as a matter of fact, you've seen some of these problems before. I mean, if I just ignore this stuff, you've seen something like that, right? That was our exponent rules from last time. How much is x to the 1/4 times x to the 1/4? Now, don't tell me how much it is, but tell me what we do. Do we add, subtract, multiply, or divide those exponents? So really what we're doing, if you think about this, we're doing x to the 1/4 plus 1/4. Do you remember that process? And we write that out, have that? Minus, we're not going to do anything here. Or here, we'll save that until the next step. Tell me, how much are we going to have if we do x to the 1/4 plus 1/4? How much is that?
X to the 1/2.
Good, because you're going to get 2/4, right? You got the common denominator already. 2/4 simplifies to 1/2. We've got x to the 1/2 minus, how much is 7x to the 1/4 plus x to the 1/4? Now I know I can combine them because I have those like terms. They have the same exact variable, raised to the same exact power. How much am I going to get here? -6, and then x to the what?
1/2.
1/2. Okay.
But you're adding.
Let's see if that works. Does that work? You need to really, really look at the similarities here. And I caught a few people already. Did you add those exponents?
No.
But for some reason, when people are dealing with rational exponents, they really, really want to add these. Something in your head goes, oh, that makes 1/2. Okay, it happens all the time. But you need to understand the process that this is exactly the same as this. If you combine like terms here and you get x to the 4th, you are going to combine like terms here and get x to the 1/4. See the similarity? That's why I show this example when I do this problem, because I really want to make sure that you see they're the same. They're the same. But people often will do this. If you look at this, try to combine x to the 1/2 and x to the 1/4. No, they're not even close to like terms. It's like saying, can you combine x to the 8th and x to the 4th? Not even close. You have to have the same variable, the same exponent. Yet, when people do this thing, they will often, because something in your head says you're adding, I have x to the 1/4, x to the 1/4, that makes 1/2. But we're not doing that. We're combining like terms. In that case, you don't actually add those exponents. You just keep them the same. You're adding or subtracting coefficients. Raise your hand if you see the difference there. Good, okay. So in our case, we're going to go, oh, no, not x to the 1/2. We're combining like terms like we did there. This should still be x to the 1/4, and then -7 at the very end. And of course, I screwed that up too. I made a mistake by trying to purposely make a mistake. Ironic. Yeah, this is what I was talking about, the 1/4. The 7 was just clearly a mistake. Now, next question. I have x to the 1/2 minus x to the 1/4. Can I combine those?
No, because it's subtracting.
That would be like doing this. Okay, can't do that. They're not the same power. You guys see the okay? Are you okay with that example? Notice how we did exactly the same process. We had one extra step because I want to do that step, show that we are actually adding, but that's.
Sorry, if that was x to 1/4, you could combine.
If this was x to 1/4,
Okay.
absolutely. Yeah. For instance, if this was a 1/16 and a 1/16, then that would be x to the 1. No, it wouldn't be the 1/8. Yeah, if that was 1/4, then we could. That's the only way we could combine it. Or if this is 1/2. Right? But we can't get 1/2 out of that.
That's trickery.
Not trying to be tricky, you know, they are the same exact exponent rules you just used here. It's just for some reason your head likes to do different things with fractions than they do with whole numbers. So fractions are tricky for people. So what? Are you okay with it? Okay, you need to track up on your own. Let's really work through these slowly. You do not have to race through this stuff. Make sure you get them right. Okay, this is one like we did last time. I want you to work on that one. And this is one we just have looked at. So of course, the only difference is here that we're writing out an extra step we would normally do in our head. It's still distribution. You're still getting rid of parentheses that way. By the way, if you ever get confused on what to do, sometimes it helps to write out a similar example without the fractions. For instance, if I forgot what to do on this problem, I'd imagine there was no fraction here and say, how would I get rid of x to the third times this quantity? Oh, I distribute. You do the same process. Just now you have those fractions, just carry those along with it. So on our first problem, we are going to distribute. When we distribute, we're taking our outside term, outside factor, times each of the terms inside our parentheses. So in our case, we're going to multiply x to the 3/5 times x to the 1/3, and then we're going to do x to the 3/5 times x squared. Did you all get the process down at least? Okay. We're just going to write that out. Just don't do it in your head, because again, what people like to do on this is they go, oh, we're multiplying. That means I multiply fractions. I'm going to get 3/15. So reduces to 1/5. A lot of people give me 1/5 on this problem, x to the 1/5. That's not what we're going to get. Instead, what we need to understand is when we distribute, yes, we are multiplying. But what it turns out is we're multiplying common bases, like that. And notice when you write it out like that, it looks like the excellent rules we just practiced. It just looks like those. Maybe you did those on your. Did you do those on your homework? If you started your homework, I hope that you did. Otherwise, you have a lot of homework in these couple days. We distribute. We have our like terms. We have our common bases being multiplied like this, and that clues in that we're going to add exponents. Then, of course, we have x to the 3/5 times, we're going to consider that to be negative 2x, we're going to minus. We're just going to write that out as well. Would you raise your hand if you made it that far and have that on your paper? Okay. Now again, when you have common bases, you don't multiply, you add those things. So do this off to the side. Take your calculator out if you like to, do this fraction off to the side if you want. We're really just doing 3/5 plus 1/3. This means x to the 3/5 plus 1/3. This means x to the 3/5 plus 2. You're not going to multiply that either. Don't add one, multiply the other one. We're adding both of them, both those exponents. So 3/5 plus 1/3, of course, we need a common denominator. You get 9/15 plus 5/15. So I'm getting 14/14. That doesn't work. 14/15. So you get 14/15 as well. So our first expression is x to the 14/15. That's our first term. Minus. We're also going to do the 3/5 plus 2. I'll erase my scratch paper here. So 3/5 plus 2. I know that 2 is 10/5. So I'm going to get 13/5. By show of hands, some people got exactly that on the paper. Good, all right. Make sure your fraction work is up to par. Again, this is not fraction class, right? We're way beyond that. We're 2 classes beyond this stuff. But if you need help on fractions, please by all means come to see me. I will help you if you're struggling with this stuff. Okay, I can't spend the time to teach you here. We're 2 classes beyond that. But I will spend some time on your own time to help you with that if you struggle with fractions. Anyhow, moving on. How do I combine these things? How do I combine those? How do I combine those? Oh. If they're the same exact variable to the same power, look at the board right now. Even if I did this, could I combine those?
No.
Even though they would have a common denominator, they're not exactly the same. There's no way to make them exactly the same. You can't do it. You're done. It's kind of nice, right? Done. Don't have to go any further. Okay, let's move on to that one. We have the same process. We are distributing. We have a FOIL situation, as a matter of fact. 2 terms times 2 terms. We're going to do the same process we did over here on our last example. We distribute, which means we multiply term by term, just making sure that we're writing out those steps, because I don't want you to miss anything. I don't want you to do this in your head, because that's when those mistakes happen. So if x to the 1/2 times x to the 1/2, next step we're going to have minus, because we have this minus, 2x to the 1/2 plus 6x to the 1/2. And then lastly, we'll get a minus 12. Did you make it that far? Good, that's partial credit right there. That at least you understand the distribution process and you've written out the steps.
Do you want to write it out like that one step?
Please. I want to see those steps. Right now we're learning it, right? Later on, when we pass this chapter, now I'm good. But for right now, yeah, I want to make sure that you guys are getting this. The reason is, if for some reason you go directly to here, a lot of people are going to give me this on the test. They're going to give me x to the 1/4. Guaranteed that this happens every year. I give the same exact problem in the test. People will always give me x to 1/4, guaranteed. So if you go directly from here to here, I know you don't know what you're doing at all. I'm gonna give you 0 credit. But if you go from here to here to here, I know at least you need distribution will be like 2 or 3 points. Does that make sense? So I need to see that. Okay, so we're back to this thing. We have x to the 1/2 times x to the 1/2. Do we add, subtract, multiply, divide those things? So we're gonna get x to the 1/2 plus 1/2. I'll put an extra step up there so you see what's going on. Let's leave the other stuff for just a second. X to the 1/2 plus 1/2. How much is 1/2 plus 1/2? We're going to get 1. Yeah, not 1/4. Just x. Interesting, isn't it? X. Can you combine these things? We have negative 2x to the 1/2. We have 6x to the 1/2. Those are the same variable to the same power. Those we can combine. You're going to get, looks like positive 4, but it's x to what power? So that doesn't change. So this is not going to give me 1. I need you to look up here at the board real quick. Understand something. If you got x to the first out of this, is that multiplying common bases is exactly the same as adding like terms, and they're not. Multiplication is not the same as addition. Therefore, you can't possibly get the same thing if you multiply. So you're saying, well, 2 times 2 is the same as 2 plus 2. Yes, it is. You're right. But not in this case, okay? So yeah, we get 4. For sure. We get x to the, it's still 1/2 though. When you combine like terms, you don't change the exponent. Minus 12. Can you go any further?
No.
Yeah, you can simplify that x.
Okay, you can if I wanted radical form, but I mean combine any more like terms at all. Then that's it. You're done on that problem. Raise your hand if you're okay with this so far. Now, there's an F word on the board. You think you're getting an F word on Mondays, right? We're going to learn how to factor using these rational exponents. Now, I'm going to do this kind of slowly. I want to make sure you really get this. We're going to do it step by step, just like we're doing our distribution. Because if you try to do this in your head, sometimes it gets a little bit messy if you're really not paying attention to what's going on. What we're going to do is we're going to try to factor x to the negative 1/3 from, now this is kind of nice about factoring as I give you what you're supposed to factor. From that, factor 7x, or sorry, factor x to the negative 1/3 from 7x to the negative 1/3 minus 5x to the 5/3. Oh my gosh, how are you supposed to factor fractions? That doesn't even make sense. What the heck? Well, I'm going to draw some comparisons to something you should know how to factor already. Factor x squared from 3x squared minus 10x to the 5th. Firstly, I want you to recognize, can you factor x squared from that?
Yeah.
Clearly. Now, I need you to understand also what factor means. What are we doing when you're factoring?
Removing.
Okay, removing. That sounds good. What are you doing when you're distributing? Well, we're not adding, we're multiplying across those parentheses. That's what you do when you distribute, right? First thing times first thing, or outside thing times first thing, outside thing times second thing. Are you looking at this, folks? You are multiplying when you're distributing. Now understand that factoring is the opposite of distribution, right? Instead of multiplying in, what are we doing when we factor? Dividing here. So what you do when you factor, here's how this works. You're going to understand this because you've done this problem before. What you would factor would be the x squared, and you'd say x squared goes out here, and I create parentheses. Now you're so good. That's how you factor, right? You put whatever you're factoring out front. Whatever you're factoring out front, we're factoring out. I can tell you, factor out x squared, you put that up front. Now, how you get the stuff in here is you take the term and you divide by what you factor, right? That's how you learned at the beginning of this class. You go, oh, okay, what I'm supposed to do is take 3x squared divided by x squared. I'm dividing out x squared. Can you tell me what's going to go right here? Now, that should be very old news for us. You should not be learning right now, right? This is just review. This is 3. If you are learning, well, okay, learn real fast. Next up, you'd have, well, whatever this term is, and this term happens when you take my 10x to the fifth, or as a matter of fact, negative 10x to the fifth, take the sign with it, divided by x squared. You see, factor means division, and we're dividing out piece by piece. What happens when I have negative 10x to the fifth divided by x squared? What happens to those exponents? Oh, you do subtract. Remember that? X to the fifth over x squared, you take the 5 minus 2, you get 3. Some people do that. What are you doing when you do that? Well, you're matching up numbers, but really you're subtracting. Negative 10x to the third is what you get that whole thing is going. And so you put minus 10x to the third. Raise your hand if you're understanding how we got all that stuff. And you can check it with distribution, right? 3x squared minus 10x to the fifth, that would be this exact thing. We're going to do precisely the same thing here. Only this time is a little bit easier, because firstly, we have exponent rules. Secondly, I tell you what to factor. That's kind of cool. So check it out. If we're going to factor out x to the negative 1/3, just like we factored out x squared, when I write my parentheses, I'm going to make that a little bit bigger. When I write my parentheses, can you all tell me what's going to go on the outside of my parentheses, please? Good. Just like we did here. What you factor out goes on the outside. That's why it's called factor out, right? You're factoring out of your expression. Now, on the inside of our expression here, what we do is we do this piece by piece. Don't ignore this step. Don't try to do it in your head, because otherwise it gets kind of difficult. We're going to do the same thing that I showed you right here. As a matter of fact, we're going to take, for our first term, we're going to take 7x to the negative 1/3 divided by x to the negative 1/3. You're taking your first term, you're dividing by what you factored out, because that's what factoring means. Let's look at that. What happens when you have 7x to the 1/3 over x to the 1/3? How much are you going to get out of this? Whatever. When you have something over itself, it crosses out, right? But I want you to think of the rule here. Listen to my voice, watch the board here real quick. When you have an x common base over a common base, what do you do with those exponents? You add, subtract, multiply, or divide. You do subtract, don't you? You go, oh, okay. This would be x to the negative 1/3 minus negative 1/3. Where are all those negatives coming from? That's negative 1/3. You're subtracting exponents because they're on top of one another. Minus 1/3. What's this minus a negative do? Negative 1/3 plus 1/3. This is x to the 0. Negative 1/3 plus 1/3 is 0. That means you would add just a 7. Or if you want to do it here, those things are gone. You get just a 7. Use that. Hey, does that work if you distribute it? Yeah. Let's try it. If you distribute x to the negative 1/3, what are you going to get? Oh, look, 7x to the negative 1/3. That's cool. That works. How many people are working on the first part? The people in the middle, are you guys okay with this or no? Yeah, okay. Now for the next one, we're going to do the same exact thing with our second term. We're going to have negative 5x to the 5/3 over x to the negative 1/3. We take the term, we divide by what you're factoring. Hey, tell me something. This one's not going to be as easy as the first one because that matched up perfectly. But it's going to be the same idea as what I showed you down here. So what do you do when you have common bases being divided? Do you add, subtract, multiply, or divide, folks? So hopefully you see that you're definitely going to have a negative 5. You all see that, right? We're going to have x. What comes first, 5/3 or negative 1/3? And you said we subtract, right? What are we subtracting?
Negative 1/3.
We're not subtracting 1/3. We're subtracting negative 1/3. You see the difference? Negative 1/3. Tell me, what happens when you subtract a negative? Do you add or do you subtract still? So you get negative 5x to the, that's 6/3. And you can simplify fractions if it's an exponent, just like regular fractions. We get negative 5x squared. That is what's going on there. Minus 5x squared. It's very similar to this process. We took the first term, divided by what we're factoring. Second term, divided by what we're factoring, that's what's going in these places. And we'll erase it so it doesn't look as confusing here.
Why you didn't cancel the x's on that one?
When you are when you're dealing with exponents, you subtract those exponents if you're dividing, and that's exactly what we're doing. The only reason why we canceled those x's here is because you're subtracting those exponents. Negative 1/3 minus negative 1/3 is 0. X to the 0 power is 1. That's why you can cross them out. It's the whole reason why you can cancel your exponents here. Here they don't match up exactly. You can't do that. How many will understand that example and understand that this is our final answer? X to the negative 1/3 times 7 minus. Okay. Try one on your own.
Will the book actually give you what you have to factor out also, or you have to find out by yourself?
It'll give you what you're supposed to factor out. But almost exclusively it's going to be whatever that is. X to the negative 1/5 times 2x to the negative 1/5 minus 7x to the 4/5 factor out. Oh, shoot. I meant to say factor this out of that. Darn it. Messed it up already. I saw a confused look. I'm like, oh, this this doesn't look anything like what we're doing. Factor this out of what I gave you next. That's what I meant. Once you get the hang of these, they go kind of quick. They really do. Once you really get the exponent rules, you know what they mean. We shouldn't be rushing through this stuff, but they're going to make more sense, start going faster through them. It's kind of nice. So we're on a factor. We're factoring x to the negative 1/5 out of this 2x to the negative 1/5 minus 7x to the 4/5. And I told you that most of the time what you're factoring out will be this expression right there, or will be one of them at least. So when we factor out, that means we're dividing term by term. So we're factoring out x to the negative 1/5. Whatever you're factoring out, whatever they tell you, that's going to go in front of your parentheses because that's what you're dividing out. That's what you're factoring. On the inside, we get those two pieces of information, these two terms, by taking our first term and our second term and dividing by what we're factoring. So in other words, 2x to the negative 1/5 over factoring x to the negative 1/5. And also we're going to have negative 7x to the 4/5 over x to the negative 1/5. Second term divided by what we're factoring. Did you guys show that on the paper? That's good, all right. Now, something special happens here. The reason why we're going to cross these out is because when you think about it, we are actually subtracting exponents. But when you subtract exponents, you have x to the negative 1/5 minus negative 1/5. Negative 1/5 minus negative 1/5 gives you 0. X to the 0 is 1. So this is basically 2 times 1. So this is, well, that's gone. Just like it works any other exponent, you cross those out because you know the exponents match up. And we subtract something that matches up exactly, you get 0. So there are no more x's, it's 1. So we have to take 2 out of that because of the coefficient included. Now the other one's a different story. The other one says, well, I know I'm going to go to 7. I know I'm still going to have x because they're not matching up exactly. But 1/5. 4/5 minus negative 1/5. I'm subtracting this exponent since we're dividing common bases. Now when we think about it, 4/5 minus negative 1/5 minus a negative, that's still addition. We're going to get how much? Okay, 5/5, or we're going to get 1. Yeah, exactly. Negative 7x to the first power. 5/5 is going to be 7 minus 7x. If you want to check the distribution, you can do it. Look at it. 2x to negative 1/5, that's that. Minus 7 minus 1/5, that's 4. Shaheen. How many understood what we talked about so far? Good, Patricia, you had a question.
Yeah, I got -1, so you always have to put the 1 from the expenses.
Yeah, you're otherwise. You're dividing this by this. We don't want to do that. We're dividing this by this. You're factoring out this. Okay, so this one has to go on the denominator every time. Otherwise, you will get the opposite sign on your exponents every time. Good question. Thank you for that one. Any other questions before we move on? I want to first remember on something. Do you guys remember how to take a root and write that as a fraction? Okay. Well, we're going to be, does the y change? But instead of just having a root around that, I should have some sort of an exponent. It should be, is it 10 over 5 or 5 over 10? 5, because we do the power over the root. So we're going to do 5 tenths. Now, can you simplify 5 tenths?
Yes.
How much is 5 tenths?
1/2.
Can you write 1/2 back as a root?
Yes.
What type of root is it?
Where?
Of y to what power?
1.
Well, that's weird. What this means is the 10th root of y to the 5th actually equals square root of y. That's kind of cool, right? This is one way that you can use fractional exponents to simplify roots. You take your root, you write it as a fraction, you simplify those fractions because that's how we know how to simplify, right? It's fractions. You write them back as a root, makes things a lot easier to do. Isn't that easier to deal with? That'll look a lot better than that one. It's kind of cool, right? Okay. We just did that just by manipulating some of these roots. Let's try this with one more. Now, does this work all the time? No, not all the time. I mean, if you had like 7 in here, that wouldn't work. You'd have y to the 7 tenths, and that you can't simplify that. However, if you can write as a fraction that is simplifiable, then of course you can simplify that. Can you write this? Ooh, that's a mess of garbage, isn't it? Can you write this as something to a fractional exponent? Let's try it. What do you think I'm going to write a to? A to what power? So what we've just identified is that when I have a root and some powers in here, it goes to both of them. That's actually one of your exponent rules. Since these things are exponents, that's an exponent. These are exponents. It goes to both those exponents. A to the 6/9, you're right. And then n to the, what do you think? Are you seeing how to get the 6/9 and the 3/9? Are you sure?
Yes.
So we have the power over root. We have power over root. Now we're going to do power over root. Where's you feel okay with that so far? Can you simplify those fractions?
Yes.
Sweet. Yeah, the 3 goes into all that stuff. So far, so good? Now, can you write that back as a root?
Third root.
Why third root?
Because that's okay.
Okay, the denominators are 3. That means that we're going to certainly have a cube root. A to what power, ladies and gentlemen? And n to what power? First. Does this represent that okay for you? So we're done.
Yeah.
Now, one thing that could potentially happen, what if one of these is simplifiable and one of them is not? Then could you write that back as one root? You'd have to make sure you have the same denominator if you're going to write that back as one root. One last thing that we can do.
How would you write it out for the final answer if instead of getting both if they're on the bottom one had like a 9 or something? Would you have to have 2 squares?
Yeah, you'd have to have 2 different roots. You'd have to have, actually look a lot like this.
Oh, okay.
However, I can show you kind of what to do with this. I'm going to. We have a square root of y times a cube root of y. Is there any way that we can write this as one root? I don't know. In order to see that, maybe we're going to translate this into some fractions, because we know that fractions are, ironically, a lot easier to deal with than these roots in our head, because we're familiar with fractions at least. So let's go ahead and let's write square root of y and the cube root of y as some fractional exponents. Everybody in here, what's the first one? Y to what power, please? That was equals to everybody. Oh my gosh. Come on now, folks. Y to the, 1/2. Time, we have times, so times. Y to what power for the next one? Okay, that's better. Hey, can you combine those? You have common bases, you have exponents. Add, spread, multiply, divide. Okay. We add them. Yeah, just like we did it, not over there. Previous example. We just did it. You add those exponents. So if we add these together, what's 1/2 plus 1/3? Can you do 1/2 plus 1/3? Well, not the way it is, but maybe find a common denominator. You can do 1/2 plus 1/3. Do it in a calculator if you'd like.
5/6.
5/6. You got 5/6? Y to the 5/6. Can you take y to the 5/6 and write it back as a root? What type of root do I have? 5th root or 6th root? Here's what this says. This equals that. You can take two roots and make it into one root. Now, why? How? One root, by the way. That was a lot in this class. Okay. How do you? What's the whole process? When you think about it, these are fractions. If you have a, look at the board. If you have a different root, what you have is a different denominator. So the process of combining roots is the same process as finding a common denominator. That's it. That's really all this is. You're finding a common root. That's the same thing as saying a common denominator. That's what you do when you combine those fractions. You make them into fractions, find a common denominator, use that to add them together. It will give you a common root. Richard, I feel okay about what we've talked about so far today.
I got a question.
Yeah.
So like, even on the previous example, if you would have 2 square roots, would that be the second step to actually get your final answer?
Yeah, except what's going to happen is most likely in this case, you probably get this back in. That's what happens. Or something that looks similar that may be reduced by a certain factor. Now, what we just did here, we kind of are simplifying these roots. We're going to take that another step. We're going to keep going on how to simplify this stuff. Are you ready?
Yeah.
Did this all make sense to you?
Yeah.
Good. Remember this stuff. You need to go back and look at this. A couple notes on how to study for, because I was talking to some students, and no one ever really teaches you how to study for math, right? You study for English, study for science, use flashcards and all that stuff. It doesn't really work all that well for math. Here's some ideas on how to study for math. First thing, studying has to be spiral, which means that you cannot just look at it once and have it perfectly in your head for the test. Math does build on itself, but we cover many, many different topics and different examples. So the week before your test, what you should be doing is going back and reviewing the first section that we covered. Every day, spend 15 to 20 minutes looking at the old stuff before you start the new stuff. Does that make sense to you? You have to do that, because you will forget it, I guarantee it. Even I forget this stuff. I forgot all about Math 4C. That's calculus. I forgot all about third-year calculus. I can't even do it anymore unless I really, really look at it. All right, and that happens for you guys, because I know that stuff. I know it very, very well. But you guys are just learning this, right? You need to spiral that information. Also, when you're studying for a math test, don't spend 4 hours studying the night before a test. It doesn't help you. Instead, what you should be doing, spend 30 to 40 minutes, take a break. Your brain cannot absorb math for that length of time in a row. So study for a little while, take a break, come back, study some more for it. Also, you need to be practicing the stuff that I give you for your review. If I give you a review sheet, you need to know it's going to be very, very similar to your test. Practice those problems. Also, when you're doing your homework and the review sheet, it should not be this way. It should be, look at my notes, do a problem. Go to the next problem. Have to refer back to my notes, then do that problem. Next problem, I have to look back at my notes, then do that problem. If you're having to look at your notes every single time that you do a problem, you do not know that material well enough. Okay, you don't. What you're doing is you're using those notes as a crutch. And I need to kick your crutch out from underneath you, okay? Ha! No, I'm just kidding, that would be mean. You need to remove that crutch on your own. Use the notes to do some of those problems, sure. You get stuck, absolutely. But eventually, put the notes away and do the rest of your homework. If that needs to be the process of skills. Does that make sense to you? That will help some of you who are kind of struggling to make it on these tests. If you do what I tell you. We're going to continue on how to simplify some radical expressions. Now, really, this simplification works on just one principle. It's just one little principle, and you guys have seen this for a long time. In fact, you've simplified radicals before. We're just going to make them, of course, a little bit more advanced for this class. Simplifying radicals works on one little rule. It's called the product rule for radicals. And here it is. It says, if you have a square root of a times b, a square root can be broken up. The product can be broken up. For instance, if I have a square root of a times b, that comes down to the square root of a times the square root of b. In fact, I showed you that before. In fact, I previewed this section before in section 10.1. I kind of told you what we're going to do. Already in this section. But this lets you solve or simplify a lot of these radicals. I'm going to put this a little bit, well, I'll give you an example first to prove that it's true by one example. Then I'll make this